Okay, there are feedback forms on the tables. We appreciate if you fill them out and let us know what you think. There are also some spare at the back, at Nick Gilboa's table there in the middle at the back, in case you're at a table and you don't have enough feedback forms. Okay, so I'll give the first talk of this session. I'm going to talk about, this is not a new result actually, unlike the rest of today. It's sort of an ongoing work. I'm going to talk about SCAPI, which is a library called the Secure Computation API. The aim is really to help. One of the big difficulties, I guess, which I'm sure, one of the big difficulties when someone wants to actually implement a secure computation protocol is that it's actually typically a very, very big project. It'll often use a lot of different primitives. If you're in a group that already has built a large library of all different primitives and tools, then it's not so bad. But otherwise, it's actually quite a big obstacle to implementing a protocol, seeing how it runs, or even trying to build an application that uses the secure protocol. This will be quite a big task, even for something which shouldn't necessarily be so difficult. So a typical protocol may use oblivious transfer, commitments also can be perfectly hiding, perfectly binding, equivocal, extractable, UC, zero knowledge proofs of all different types, circuits, and so on and so forth. And there are general cryptographic libraries like Crypto++, OpenSSL, Bouncy Castle, but they're very focused on secure communication. That's what they do. So they give you encryption and signatures, key exchange. Depending on the library, how easy it is to find the low-level operations that you want to do, for example, in a group. Some are easier, some are harder, but it's definitely not the focus of what the library is there to give you. There are libraries for secure computation that have been written, but most of them, and I'll say most, are either not open source or they're not maintained and supported. In other words, sometimes a PhD student did a very good job, wrote a library, graduated, and then the library sort of ended at that point. And also some of them are very suitable for quick prototyping, but if you want to build something a bit more robust, a bit bigger, then it'll be difficult to do. So I'm not saying that SCAPI is the only library out there, but I think that most of them fall under those categories. If not, then I'll be happy to hear about them. Most academic implementation projects also are aimed at solving a specific problem. We have a paper with a new protocol. We want to implement that protocol. We write something quick and dirty that'll be fast, that will show how we perform. But the aim is not necessarily reusable, or is typically not reusable code that other people can use. SCAPI is completely different. The library is not there to solve any specific secure computation problem or for supporting any specific paper, but it's really supposed to be a general purpose secure computation library or even infrastructure. So it's an open source project. If you go to this link at GitHub, let's see if it works when I open. I don't know, whatever. It's at GitHub, so it's at it's a fully run as any open source project. You can download it, you can have a pull request, you can report bugs, you can ask for additional features, all supported on the GitHub website. We have a long-term commitment to the library. In other words, we'll provide support to people who want to use it. So if you have questions, problems from installing, or you find bugs or anything to that effect, our aim over time is to improve existing functionality, improve existing implementations, more efficient, more secure, etc., and also add additional functionality, more protocols, more primitives. Currently, the focus is pretty much on honest minority type tools. Don't have so much of the secret sharing type tools. That's, for example, one big area that we definitely will want to go to eventually. But building such a library takes a very long time, so it's a lot of work. We're also very happy to receive code contributions. I think that for this library to really succeed, it's something that should become something that the community does rather than us, and then we can maybe really have one place with a large variety of different tools when someone has some new implementation, they can add to the library, and it can really become something which is general purpose and helps everyone. It's written in Java, which we can argue a long time, is this a good idea or not a good idea? It's sort of a compromise, I guess, between Python and C++. So it's suitable for large projects and for reasonably quick implementation. It's portable, so you can take the same implementation for a PC and put it also on a mobile. And there are also a lot of existing libraries that can be used. Of course, one of the big problems with Java is that it's much, much slower than writing something in native code. So the JNI framework helps a lot with that. So typically, or not typically, unless you're running on a mobile where you want something which is pure Java, you'll use JNI to call native code which will do smaller operations. The trade-off between how much you're getting in terms of how much you're losing in efficiency depends very much on the protocol. I'll talk about that a bit more later on. But just to give you an example, so if you want to do an OT extension, then one possibility is to write it in Java and just use the OT calls in native code. That will actually not be a good idea, because there's a lot of intensive work which is happening beyond those calls. But if you want to do implement an oblivious transfer that uses exponentiations like PVW, then running the protocol in Java by just calling the native library to do exponentiations actually will give you something which is very, very, very efficient. So it depends very much on what you're doing. We use libraries. We've wrapped and incorporated libraries. So we've OpenSSL, Miracle, Crypto++. A lot of that low-level functionality is wrapped inside SCAPI and so is available for use with the very high efficiency that it gives. So what are the design principles that we use when we build SCAPI? So one was flexibility. When we write a paper on and sort of flexibility and also speaking in the language that we cryptographers typically like to speak in. So we'll talk about in abstract terms about oblivious transfer, commitments, pseudorandom functions. And SCAPI actually encourages implementation at this abstract level. So it defines the interfaces which represent cryptographic primitives, and then a protocol that uses oblivious transfer, a commitment in, say, a group where a DDH is hard, can actually just take objects of that type. And so and if you have a DDH group or a DLOG group, as we call in the library, then it enables you to exponentiate and actually doesn't care. You shouldn't care whether it's an elliptic curve group or prime subgroup of ZP star. It doesn't make any difference. The interface is the same interface. And so actually your implementation looks much closer to what the protocol itself looks like when we write it down in terms of the type of interface. And then the application who will call the protocol. So I have now, say, a protocol that uses oblivious transfer, commitment, and some group. Then essentially the constructor of the protocol is supposed to receive one of each of these types, and then you'll decide, the application will just decide at that point which one it wants to use. So I want an elliptic curve group of a certain type, say P256, and I want to use PVW transfer, and I want to use Ivan's brand new commitment, and I construct one of each of those and pass that to the constructor of the protocol. And the protocol itself is completely oblivious to what it's actually receiving. It doesn't care. And so also it's very easy to compare what the ramifications of using one commitment versus another is. So I'll give you an example of something that Ben will talk about. He's going to talk about part of it later on. We have an implementation of this, the new online-offline YAO. And one question is how much will replacing the garbled circuit with another one which is based on more standard assumptions, how much will that affect the actual running time of the protocol? Will it make a big difference or not make such a big difference? When it's implemented in SCAPI, it's actually very easy to do that test. It's almost for free. So that's a big advantage of working at this abstract level. So the protocol can also receive primitives at different levels of abstraction. So you could write a protocol that will work for any pseudorandom permutation, or you actually may specifically want to use AES, or you may actually specifically want to use AES from OpenSSL. This is up to you when you design your protocol at what level of abstraction you want to write it. Obviously, it's best to use the highest level of abstraction possible, but your protocol may actually specifically want AES or specifically want elliptic curve group and not another group, in which case you can actually do that as well. As I mentioned beforehand, so once you're working at this level of abstraction, the protocol code itself is independent of the actual primitive. You can compare the ramifications of running on different elliptic curves or different groups. So it turns out that indeed if you're using something like ZP star, 1024 bits, then actually that's more efficient than most elliptic curve groups. But once you go up to 2048 bit, then the elliptic curve groups are all much faster. And this is really, really easy to see within SCAPI. Just it's you change one line, as I'll show you later on. The same code also said can be run on different platforms, which is an advantage. And one of the biggest ones is that you can add primitives or libraries later on and just take that functionality by writing a wrapper for SCAPI, and the advantages of this new library will automatically be built into your new protocol. And that's a big advantage as more implementations and new libraries start coming out. When we compare primitives, so one thing that you might always think, well, just take the fastest one possible. Why would I want to even have all these different options if there's one which is the fastest? And the answer is that different primitives have different advantages and disadvantages. So because there is often a trade-off between speed and security. I may be using stronger or less well-established assumptions, and so a comparison on how much of an effect it really has to use this less standard assumption is a good thing to know. So, you know, most people in this room, I assume, will live reasonably well with a random oracle when it's needed. If the next best alternative is really bad, then we'll pretty much live with it and we'll say, okay, not you run Canetti, I know, everybody else I meant. But what happens if we actually find out that using the random oracle only saves us a fraction of a second? Then I think many of us, I don't know how many, we can maybe take a poll later on, many of us will say, well then let's not use the random oracle because it's actually not saving us too much. So being able to compare and plug these different things into the implementation and make that decision is something which I think is worthwhile. There are also other things which are more subtle, like it depends very much on the type of operation. So a Koblitz curve, for example, is much better for faster multiplication. But when you have a fixed space, like fixed-space exponentiations in a D-log group, then actually it performs less well than other types of curves. And so you know, you have a protocol which is a whole lot of different things, and you can try and calculate theoretically what's going to perform better, but it's often very hard to know. And this way you can run different tests and you can see actually what's better for your actual protocol. The second design principle is extendability. So it's a general infrastructure, and we can add new implementations later on. Every primitive has an interface. A new primitive will just be a matter of defining a new interface for it. And any future implementation of an existing primitive will just have to implement the interface, and that's all. Sorry, what happened? Yeah, OK, so let's take an example of oblivious transfer. Before PVW, oblivious transfer for malicious adversaries was horribly inefficient without a random oracle, although even most of the random oracle protocols before that were not fully simulatable. But so you would write a protocol and you would have using oblivious transfer, but this would be your bottleneck. But then PVW came along and suddenly it became much more efficient. And then you were using PVW until today, but now today we have really efficient, or until TinyOT, when you had an OT extension that was maliciously secure. So you now used the TinyOT OT extension. And now Gilad today told us is actually a new protocol which is twice as fast. You don't have to change anything inside your code. All you have to do is take a different OT to plug in. So the OT and OT extension actually have the same interface, so everything works in exactly the same way. So your protocols sort of don't become out of date so quickly. In terms of libraries, as I said, we support currently OpenSSL, Crypto++, Miracle, and Bouncy Castle. And we can do anything later on as long as you can wrap it. And we get the efficiency via JNI, so wrapping essentially means writing JNI for that lower level library. In terms of efficiency, so this is the big thing, right? So it's clear that if you write your entire protocol in C, you're going to get higher efficiency. And so there's a trade-off here. If you write with SCAPI, then you'll still get a fast implementation, but it'll take you less time to implement and be more modular than if you were to write the whole thing in native code. Also, it'll be easier to reuse later on. So there's a bit of a trade-off. I would say that if you're writing an application that uses SCAPI computation, this would probably always be the best choice. And other things, it depends very much. But the project that Ben will talk about later on this afternoon with the online-offline YAL is actually written in SCAPI, and we got very good results with it, although some parts we had to further optimize. So depends very much. SCAPI will also have some things which are like an OT extension or a garbled circuit. That sort of thing has many, many, many calls to a primitive. If we were to use, you could do a garbled circuit. There is implementation in SCAPI that does the whole garbled circuit in Java, but just calls a double encryption for each gate in native code, and that's obviously not very efficient. So all the other possibilities also available, which is very fast garbling, which is all written in native code. So those things are all already inside SCAPI, so you can get very fast garbling, very fast OT extensions. Okay, ease of use. That's also one of the things that was very important to us. So the aim of the design of the library was for secure computation. So again, it uses the type of language you're used to. You don't have to dig deep inside some library which is meant for encryption to find how to do an exponentiation. And you don't have to make a decision about what type of group you're using when you first implement, which is, for example, in Miracle, if you're using a binary curve or a prime order curve, it's actually two completely different set of instructions. And so once you've written that, then changing it is going to be a huge pain. It's documented, commented, and we hope that it's well written and clearly written. At least that's the aim. we're sure that there are bugs and things that can be improved, but this is a work in progress. It has has documentation, so that's the link to the documentations. There are tutorials there, how to install, how to use your first SCAPI project, etc., etc. So we're really trying to make it easy for people to use. So here's a bit more cryptographic side. So let's say I want to write an oblivious transfer protocol that uses a group, a commitment scheme, and a hash function. And my theorem says that if the DDA, if the decisional differential assumption holds in the group, and the commitment is perfectly binding, and the hash function is collision resistant, then my protocol is secure. But how can we differentiate in the library that we're actually getting a group that is appropriate? So DDH is hard and not just CDH. How do we know that we're going to get a commitment that is perfectly binding and not perfectly hiding or something else? And maybe, how do we know we're getting a hash function that's collision resistant? Maybe we'll get something that's weaker because, again, the protocol itself just gets a commitment. It doesn't know exactly what it's getting, and that's how you get the modularity. So we have security levels, which are essentially, same question again. I want to use a protocol that can work with any non-malleable CCA1 secure encryption scheme. How can I make sure that I get that? Can I use Kramer-Shoup? Well, it's CCA2, so we know we can, but how can we model this inside? And the idea is we have hierarchies of interfaces for security levels. So on the left-hand side, you can see the hash security level, and there's target collision resistant and collision resistant. For D-log security level, you have discrete log, computational differential and decisional differential. And for encryption security levels, you have indistinguishability and non-malleability, which are two different goals. And you also have eavesdropping adversaries, CPA adversaries, and CCA1 adversaries, and CCA2. And you can see that if you're CCA2 secure, then you're always going to be both non-malleable and CCA1, and this will automatically be recognized by the library because you have this inheritance. So if I want something which is, my protocol needs a non-malleable CCA1 secure scheme, then the first thing it does in the constructor is check that the interface that check the encryption it got indeed is non-malleable with CCA1. But if that's Kramer-Shoup, it's declared to be CCA2, but that's fine because it inherits from both, so it is both non-malleable and CCA1. Likewise, if I need a DDH group, then I'll just check that within my instantiation. And we have also for other things as well. SCAPI has 3 layers: basic primitives, which is all the very low-level stuff; non-interactive schemes, that's like encryption and signatures; and then interactive protocols, which are in the current release. That's a bug. So most of the code at the lower level is wrapping low-level libraries. There are some exceptions of things we implemented ourselves, like HKDF, which is Hugo's key derivation function, universal hash, Lubirakov, and some more. And again, I mentioned this before, and so I'll skip it. So we have pseudo-random functions, permutations, all the things you would want: hash, universal hash, trapdoor permutations, PRGs, key derivation, discrete log groups. That's everything you would expect. The next level for non-interactive schemes, you have, again, the schemes you would want, like RSA and El Gamal, like Kramer-Shoup, Damgard, Yurik. All of these sort of things are there, so they can be used automatically because they're all already implemented. And in the third layer, which is interactive protocols, that's the things that we really need for secure computation. So one thing we have is Sigma protocols, and there we have over 10, I think there's like 10 to 15 different common protocols with proofs relating to DLog and DDH and Uric Damgard and more. You can take any set of Sigma protocols and do ands and ors over them, and you'll get back another Sigma protocol, which you can then transfer into zero knowledge, or zero knowledge of proof of knowledge using interaction with standard assumptions, or you can do Fiat Shamir to get non-interactive zero knowledge. You can also transform to a UC zero knowledge. So all of that is inside already. Commitments, there's a series of commitments. I'm not sure if all of these are in here. I'm not sure that all of them are yet implemented, but most of them are. For interactive protocols, you have oblivious transfer. You can use semi-honest, which is Noah Pincus, and the OT extension, also semi-honest. For malicious, you can take a privacy only, one-sided simulation, full simulation, UC secure. All of these things are inside. The OT extension that Gilad presented this morning will be added soon. There are garbled circuits inside the library, a basic one, also an optimized one, which is all in native code using fixed key AES and the ASNI chip. And there's coin tossing as well with 3 different security levels for that. Our plans for the future are to, as I mentioned, to improve the existing protocols, both in terms of when we find errors and improvement in efficiency and in the security if we find problems, adding new functionality, and improving the overall infrastructure. So for example, the communication layer was just recently rewritten. Initially it was just a socket base. Now you have a choice between a socket and a queue. For those who don't know, which I didn't until recently, a queue just gives you a much more robust communication. So even if something falls, it'll come back up automatically, and you won't lose anything. So for bigger projects, a queue is actually very, very advantageous. All of this, you can also automatically just add SSL into it if you want authenticated channels, which you probably want. So here's an example. With the time that I have left, I'll try and give you a couple of examples of how something would work. So this is how Kramer-Shoup looks. It uses takes a DLog group and a cryptographic hash, and it takes a random source. And then what it does, the first thing it does in the constructor is it checks that the DLog group is an instance of DDH, and that the hash is an instance of collision resistance. So it's checking that the security levels it's getting is actually going to be correct, and if it is, then it just initializes the variables that it needs. And then when you encrypt, you do things that you would. So here it's a bit more complicated because it's sort of trying to save on repeating code, but you have DLog group exponentiate and multiply group elements, and then map any group element to a byte array. You can map group elements to byte arrays and back and forth. So it's really speaking the way that we would like to implement. And then you can take. You can write a small program which will run tests on how efficient this is for all different types of groups, and you have a configuration file which will define the group that you want and the hash function, and then you can run that and you'll get this table which will show you with very little effort all the different times running for different groups on different libraries. So obviously Bouncy Castle is going to be much slower because it's pure Java. Crypto++ and Miracle will be much faster. And OpenSSL will probably be even better than all of these. And this is sort of really easy to do because you have one implementation and just plug in different groups. So here's another example for a garbled circuit, which is, again, you need a random source. That's up here. I don't know if you can see this. And then you generate a garbled Boolean circuit. You get given a file which describes the circuit. These are parameters about if it's freaks or other things. And then you just type fast garbled circuit.garble with the seed. This is garbling with a seed, so you take the seed and then garble with that. So verification is easy. By the way, the garbling interface has verification as part of the interface. So if you want to check, you're given a seed now and a hash of a garbled circuit from one party. You want to check that it actually was constructed correctly. You just have a function called verify that you just need to call, and everything is done for you. Also, there's a basic garbled circuit, an extended one. In the extended one, you can do things like decide externally what the input keys are and the output keys are, because depending on the protocol, sometimes you need that. Another example, if you want to do a Sigma protocol, so here this is zero knowledge from Sigma protocol. You just define, again, you need a random source, and you need, so this, yeah, so here, for example, sorry, you construct a prover, you take a D-log group, T is the parameter, the security parameter, and then you can just, you take a Pedersen commitment, and you define the Sigma protocol prover using the commitment and the basic original Sigma protocol prover. Now you have full zero knowledge. So you don't have to do this yourself. This is already done. But if you want to do zero knowledge from Sigma protocol, it's very, very easy. Just plug it in. And then if you want to change, if you want to do a different proof, you just have to, for example, this is for a Diffie-Hellman verifier or prover, or Diffie-Hellman extended, which is when you have larger tuples. So all these things can be very easily plugged in. OK, so in summary, SCAPI is an open source library. The focus so far is on primitives for the no honest majority case. And we don't have that much secret sharing stuff. So things like speeds, we don't have the tools for that yet. But it's not because we don't want to. It's just a lot of work. I think you can appreciate that. So we're very interested in collaborating with the rest of the community to make it into the bouncy castle of secure computation. I think that would be in everybody's interest. We have a long-term commitment to it. I can tell you that for the next 5 years, we have money to continue supporting it, and I hope it'll be after that as well. And if you use it, we'll be very happy to collaborate with you and help you. So thank you.